I mean, I spelled that right.
Okay, just a reminder, on the property sheet, you should have a box around these particular trig functions. If you haven't already, did everyone get a property sheet? Everyone should have them, correct? If you haven't, you've printed one off. Okay. All right, those, you should have a box around those. Now, yesterday, I hinted at the fact that we did the first one where we did a couple problems where we had to substitute sine, cosine, and for tangent. We did a couple of problems where we substituted 1 over like sine or 1 over cosecant for the trig functions. And I think we ended the day with a Pythagorean identity problem. We did one of those. The goal today is to look at the evens and odds problems. So we're going to look at one of those, and I know it seems weird that you guys sit in pods. We're eventually going to try some problems out by yourself or with your group, and we're going to see if we can actually finish the problem, see if you can do one. Okay? We're going to start with easy problems today, and then we'll work our way to the more difficult ones. First class that tried this today, they really struggled with it. They weren't paying attention today, and they did not like it. So they were not paying attention the last couple days. They didn't take any notes. It's tough. Like, it's not meant to be easy.
You only have 2
So yeah, this morning they did not like it this morning because they weren't paying attention, and then I threw them in the deep end. So
you dirty dog.
So all right, let's go to the.
Who's the worst in that class?
Hey, we're going to go over these evens and odds. I want to explain why these actually work, why they have negative signs, why the negative signs go on the outside versus inside, why some of them cancel it. I want to discuss it. Those are called evens and odds functions. Let me get rid of this graph here, my little table. Okay, on an even and odd function, I'm going to look at the first one. I think it was the sine function. Sine of negative x equals negative sine x. Right? That's the problem, correct? That's your property on the bottom. That's the even and odd property, correct? Or read it correctly?
You should know your pre-calculus.
I'm asking you. Can you find it?
Yeah.
Okay. So, what you're looking at here, this function is considered an odd function. Now, let me explain what an odd function is. An odd function, if we remember back to, geez, it was like late September, early October. Evens and odd functions are when you look at a graph and the answer is the complete opposite answer when you cross the y-axis. So what I mean by that is if we were to draw the sine graph like the wave function that we did back in the last chapter test, okay? On the last chapter test, these were the sine graphs we had to draw. Right? We went up to the top, went down, came up, and that was what our sine graph kind of looked like. And we had all the markings made. Well, what I didn't tell you is if we were to draw this drawing continuous, that was one period length. If I were to continue to the left and actually continue this drawing and put 4 hash marks going this way and actually continue that drawing, this is what it would look like, right? The idea is that when I picked an angle on this side, let's say like 30 degrees, and I picked negative 30 degrees, they would actually give me exact opposite answers. That's why it's considered an odd function. They would give you exact opposites. That's what they're actually saying here. When you plug in a negative 30 into your angle, your answer will be the sine of 30 degrees, but the negative sign will be on the outside. It will be the complete opposite answer to whatever the sine of 30 is. Because when you actually look at the graph, it explains it. This answer was negative, that answer was positive. They're opposites of each other. Does that make sense now? Like what it's doing. Now, when you look at its reciprocal, cosecant, if you look at cosecant on that bottom of your property sheet, and they have a little negative sign. When you look across from it, it should have the negative sign on the outside, correct?
Yep.
Because cosecant is also odd. Its reciprocal is still an opposite. It's still an odd function. Because how you actually draw cosecant is you put the asymptotes in here, where it hits zeros, and then you just go the opposite direction off of these graphs, the peaks and valleys. And the graph shows you that it's odd. Okay, when you pick negative 30 and you pick positive 30, the answers are opposites of each other still. It is still an odd graph. The numbers are across from each other. When you look at cosine, cosine's answer, when you have cosine, the weird thing is cosine's answer actually cancels the negative sign out. Agreed? When you look at cosine, the negative sign goes away. The reason being, cosine is considered even, not odd. When you actually draw cosine's graph, and you actually draw the right and left side of it, Morgan, you are, I guess you can join either one of these two groups.
Sounds good.
So keep them kind of even. All right. When you draw cosine's graph starts at its peak and goes down and then comes back up again. Well, when you actually continue that graph on the left side, you can see that the answer is the exact same on the right and left side. So that's why it's considered an even function. That when I picked positive 30 and I picked negative 30, the answers were straight across. They were the same exact answer. That's called an even function. That's why when you plug in a negative angle into cosine, you get the same answer as if you use the positive angle. They give you the same result on a calculator. So negative 30 versus positive 30. They give you the same result. They're equal to each other. Now the answers could be negative, but they're going to actually be equal to each other. Well, these set up here, the answers are actually opposites. Okay, now why this is important. There is problems that we're going to be seeing eventually. Probably, I don't know if we'll get one today, we might. Where when you're doing a problem, we're trying to simplify a trig function down that's somewhat difficult looking. And we're trying to simplify it down. If they have negative signs in the problem, we can start to get rid of them in certain cases. Like if there's a negative sign on the inside, you can get rid of it. If it's a negative sign on a sign, you have to put it on the outside, and you can start factoring all those negative signs apart. That's something that we need to think about. Okay. This is just something that we are eventually going to get into. It's something that a lot of people won't think about, evens and odd functions, because we haven't really discussed it yet until now. But that's something I want you to be well aware of before we move on to these examples today.
Did you get this card thing from Mr. Meyer?
No. So. All right. Questions on the evens and odds functions. Okay, perfect. All right. Next. All right. We're going to do an example today because there was one problem I did not show you an example of. Okay? And the example that I have not shown you as of this moment, because we did yesterday, we did problems where we had replacing sines and cosines and problems like with tangents and stuff. We had problems where we factored things apart. We're actually going to look at one of those today. We had problems where we combined fractions. I want to maybe bring one of those back up today. But the one rule we haven't discussed is conjugate rule. That's a rule we haven't seen yet. We need to discuss it, and we need to do an example of it. This is one of the examples that I've been kind of waiting to show you because it's kind of difficult looking. So here we go. This is a problem I'd like you to write down. 1 plus cosine of theta over sine theta plus sine theta over 1 plus cosine theta. Okay, my goal is to simplify this thing down. That's always the goal. Maybe this is like one of your problems you have in the homework where they want you to evaluate it. Maybe they tell you what the sine of the angle is, or the angle's 30 degrees. You could plug in all the 30s and go and evaluate what those are, try to add them up. That would take a long time because you're going to get fractions everywhere. You're going to have to try to add the fractions together by getting common denominators. You're going to have to, do reciprocals eventually because it's complex. There's fractions over fractions. It would be a nightmare. It'd be a lot of work. What I would recommend is before you start the problem by evaluating it, actually simplify it with the rules I'm showing you. Okay? Because it can make your problem easier to look at and faster to actually answer later. It doesn't waste so much time in the beginning. Okay, so what I mean by this is on this particular problem, when I look at it, do you agree that everything's in terms of sines and cosines?
Yep.
Okay, so I don't need to do any substitution. There was no tangents or anything in there. So that's good. There's nothing I need to really factor apart, but I do need to combine these fractions. The only way I can combine these fractions is if they have the same denominator. Right now, they most definitely do not have the same denominator. So at some point, we'll need to get there. But do you notice on one of the denominators, there's a binomial down there, the 1 plus cosine? We need to make sure you get rid of that. I don't like to have binomials on denominators, so we want to get rid of that. So what we have to use is this rule. It's called the conjugate rule. Okay, a conjugate is when you have a binomial on the bottom, like this, something like this, where it's not factorable, and it's not. We can't just do a Pythagorean identity substitution, which I'll show you here in a minute. So if you ever have a binomial on the bottom, here's what you need to do. You need to take this fraction and you're going to multiply it by its conjugate. Now, if you don't remember what a conjugate is, we talked about this earlier in the year. You just take the bottom, whatever it is, and just put a negative sign on it. That's all you do. So it's 1 minus cosine. And this is 1 minus cosine. You're going to multiply the top and bottom by the same thing, because you're actually multiplying by the number 1. Okay, and what you're going to have to do is on the top, do not distribute the top. This is my little rule. If you ever choose to do a conjugate, do not distribute the top. Your what?
Back there.
Back there? Perfect. There you go. Do not distribute the top. Only FOIL the bottom together. It's a weird little quirky rule with conjugates that if you FOIL the bottom together, it'll actually work out nice and pretty in the end. You'll see it here in a minute. That's just how they always work. On this side, I don't need to do anything with this. There's not a weird binomial on the bottom. I'm going to leave that left side alone. So over here, I'm going to leave this alone. 1 plus cosine of theta over sine theta. I'm going to leave that alone. We'll use that here in a minute. On this side, I told you not to multiply the bottom. So you're going to leave this alone. So we're going to leave that numerator alone. On the denominator, though, we're going to FOIL that all out, and it will eventually simplify. Okay, so can somebody FOIL this together for me? First, outer, and last. What do we get?
1.
1, 2.
1.
Yeah, 1.
1 times 1.
1 cosine. What are minus?
Negative cosine?
Okay.
Plus cosine, yeah, because some people are kind of doing it different. That's fine.
And cosine.
Negative cosine squared. Yeah, so it looks like you guys have the basic factoring down, right? First, outer, inner, last, FOILing, I should say, where you go 1 times 1, 1 times a negative cosine, cosine times 1, and then negative cosine times negative times positive cosine, which is negative cosine squared. Now, what happens to the middle terms?
Cancel.
Yeah, these are gone. That's why we want to FOIL. That's why you actually choose the conjugate, because it will actually cancel those out. So the denominator is actually just 1 minus cosine squared. Okay, does that make sense? Like that's what the denominator is on that side. Now, that part right there, I know it looks goofy, like it looks like I just made it more difficult looking, but that denominator now is actually a Pythagorean identity.
Why is the square not after like the circle?
Sitting?
Why is the square not after the circle?
You only put the square after the circle, like after the theta, if you're squaring the angle. If you're squaring the whole item, like cosine times cosine, you put it before so it doesn't look like you're squaring the variable. So it's just a way of like abbreviating so you don't get it wrong. I've actually seen it written like this before. I've seen it written like this, like cosine of theta, and then squared. I've seen that. So you could do it that way so you don't get it wrong. They just put it on the inside so it doesn't look like you're squaring the theta. Alright, but anyways, that 1 minus cosine squared, that's a Pythagorean identity we can sub. So if you didn't look at your property sheet yet, we talked about this yesterday. There is a property on your property sheet called the Pythagorean identities, which this is one of them. This is one I think we did yesterday right before the end of class. Sine squared plus cosine squared. You're allowed to use any manipulation of that Pythagorean identity, and you can substitute in. That is one of my rules. Typically, after you use a conjugate, after you do a conjugate, you typically will follow it directly with a Pythagorean identity. That's how they always work. That's why we choose to do conjugate rule. What I mean by this is I can use any manipulation of this. I can move these items around and still get something I can substitute in. So like for instance, if I move this cosine to the other side, what happens to it?
Negative.
It's negative, right? So it's 1 minus cosine squared. Well, when I moved it over, that's just equal to sine squared, right? Because that moved over to the other side. This is actually what you're seeing down here. So I'm allowed to take off that denominator, the 1 minus cosine squared, and substitute something of equal value in, which is that sine squared. So this is what I should have as of this moment. So this side I haven't messed with that left side yet, but the right side is this now. And there's a reason why I didn't FOIL or distribute the top. You'll see it here in a second. So I took the denominator out, this is the denominator down there, and I replaced it with sine squared. That's a Pythagorean identity, right? Any manipulation of it. Now, can anyone point out why didn't I FOIL the top together?
So you can get rid of the sign.
Yeah, the signs will cancel. If you FOILed, if you like distributed the sign through the top, you'd actually have to factor it back off again, so it cancels out with one of the signs on the bottom. There's actually signs top and bottom. And why I'm allowed to cancel these right now, why I couldn't do it later, is because now these are being multiplied together, and you're allowed to cancel things when they're being multiplied, not added or subtracted. So now that I have this, I can get rid of one of the signs on the top, and I get rid of one of the signs on the bottom. And when you do that, now this problem will have a common denominator, and I can add them together. And I know that seems like crazy, that, you know, like it's a long process, it seems, for doing this. But it's actually easier doing this work than actually trying to plug in 30 and evaluate every fraction by themselves. It does work out actually faster, and you'll actually see that my answer is just really simple. Okay, so I canceled the sign on the top, I canceled one of the signs on the bottom, and now do you notice that I have the same denominator?
Yep.
So now I can add them together. So if I want, I can actually add straight across, and you only add the numerators together. And when I add the numerator, the denominator will stay the same, it will stay the sine theta. But when you add the top, the cosines go away. One's negative, one's positive. And so I'm left with 1 plus 1, which is? 2. That is technically your answer. Now, if you want, like because that's one single fraction, it's a single trig function, you can actually just do a shortcut where you can just move this sign to the top of the fraction and just choose its reciprocal. That's how you just flip it really quick. Move sign to the top, and what's the reciprocal of sine? Cosecant. That's your answer. It's one single trig function. It has a 2 out front. So if you go to your triangle that has 30 degrees in it, rattle off what the cosecant of 30 degrees is, take it times 2, you're done, that's your answer.
Oh,
Like,
yeah. Have to do that?
this work is the type of work that we need to be ready to handle. Now that problem is difficult, don't get me wrong. That's the deep end. I'm throwing you right in the deep end to show you kind of what we can use this for. But again, why we choose to do this type of math? This is for somebody in like an upper level calc, pre-calc kind of frame where they're trying to find rates of change on slopes, they're trying to find derivatives, they're trying to find any type of ratio between certain trig functions. And this is a process we use to just simplify the problems. Because these are very difficult looking problems, but we simplify them and make them easier to calculate without a calculator. Because this stuff that we're going to be doing doesn't need a calculator. It doesn't need one. Because we're not going to be evaluating too often. We just need to simplify it. Okay, because I would hate to try to plug in 30 degrees in here and then try to simplify all that answer down when I could have just done that instead. Now, why could I just move the sign to the top? Because technically, because I don't like to have fractions as my final answer, I was replacing the sign with this. This is the same property in your property sheet that I could replace it. And then you'd have to do a reciprocal, because I'm technically divided by this. So that's why it just flips over and it goes to the top. My shortcut is just, if you have a trig function on the bottom, just drag it to the top and make it the reciprocal. There's a lot of process there. Okay, I know that seems difficult. What we're going to do today, you guys in your little pods, each pod has a certain number, right? There's 4 groups in here, technically 3. I'm going to hand your group one of these envelopes. They have 2 problems in there. You can pick one. And I just want to see if your group can figure out how to simplify it. All of these problems will either go down to a single trig function or a single number. That's all it is. And I want to see if you can handle it. First class could not. They did not follow my notes.
No, we're going to do it easily. Watch us.
Are we doing all 3 of
Oh, I
these?
think he gave us group 3.
Eventually. Today we're just going to go.
There's only one. Oh, never mind. Pick one.
There's 2 problems.
Let's do 4.
So which one do you want to do?
Literally pretty much up there.
So pick one of them. You just need to simplify it as fast as you can using the simple rules that we talked about. Okay, you want to get down to a single trig function or a single digit, a number.
Okay.
It's equal to
So-
sine squared. It's equal to sine squared.
Okay, so that would be
Oh, so you start you?
Right, it's sine squared.
You're down to a single
1
trig
plus
function.
cosine.
We're up to today then?
We're done.
There you go.
We'll talk about what we're going to
Do we have to do this one now too?
Times different foil.
do. If you want, like, if they're going to be well, you you don't.
And then
Plus.
Like what I'm looking at right now is the top rule.
Oh, but at least you guys recognize.
Why have you taken that?
minus
Hey Ward,
2 Asians, Morgan,
I have this cosine.
can I run that plate to advance room really quick?
so you have 1
2 Asians.
2 Asians, Morgan, and Ray.
squared.
So,
And then do you do chord?
Yeah.
So I think we just kind of put this on the last thing.
Which one?
Me and Shrews
It's
are not.
like sine,
How do you guys end up in the scene? How's that?
sine squared plus cosine
Both
squared
your
equals
aces.
1. So
Okay,
if
secant.
you
What
separate
are you guys doing now? What is secant on that property? Go look at the top row. Yeah, what is secant?
So it says sine squared plus cosine
Write that
squared equals
So
1.
1 over cosine.
So if you
Yeah.
just move the negative cosine.
And the other
or
one's
move
in
the
terms of
cosine
sign already,
over,
so just leave it
it's gonna
sign.
be sine squared
Because you don't,
equals
because I always want to
1
put things in
minus
terms
cosine
of
squared.
sines and cosine.
Like where are we now?
Okay,
Do you not see
multiply
it?
together. What do you get?
That
We
first
figured it out.
First one?
Yeah.
We haven't finished.
1 sine over cosine.
1 sine over cosine. Okay, agree, write it down. Okay.
Write down.
This one, right?
Wouldn't that just be
Yeah.
1?
No, it's negative. Because you switched.
And sine over cosine equals to 1.
You said this tangent minus secant.
Tell us. So now we're just like
See,
a
we're
tan.
already smarter than the first class. That was, we got that done in like 5
Trust me, it
seconds.
was like
Okay,
one
we're
deep.
finished.
We did it.
5
You got it?
seconds. Come at us.
Yes,
What?
that's what I want.
Come at us.
Simple. Okay,
I see you
Now,
guys.
okay, everyone's getting it? All right, hey, I'm actually really happy with that. Now, I want to do one more example, and then we're done for the day. Okay, what I'm talking about here is, you guys, believe it or not, did almost the same type of problem, all 3 of you, all 3 groups. It wasn't the same exact answer, but your style of the problem was the same. You were replacing sines and cosines, or cosine squares, into those problems. You're using either a Pythagorean identity, or you're just doing the simple manipulation of reciprocals. Okay? What I want to show you is, if we put all 3 of your groups together and we did one problem, what could it look like? Did you guys figure that out fairly quickly? Once you got started, you guys got the flow of it. I want to show you a problem that we can mix all 3 together. Okay? So here we go. Good. Okay. So let's talk about the one problem that we can mix all of your groups together, because you guys did figure that out very, very quick, which is really good. But now I want to show you what we can all use that for. So I picked a problem out of the book when I was picking these out that kind of mixed all of your styles together. And it was one problem. Where is it? It's group 4s. Okay, here it is.
That's my dad's
1 minus sine squared theta over tangent squared theta. Okay. This one problem mixes everything that you guys had all in one problem. All in one. Okay? So what I mean by that is that there's a bunch of different ways you can do this problem. One of the ways that, that you could do it, you could start with making the fractions have the same denominators, and then you can subtract straight across. You could do it that way. Some people, when they first start, they want to replace everything with sines and cosines first. We could do it that way. It's kind of up to you guys. What do you guys want to do? You want to make common denominators, or you want to go sines and cosines?
Which one's faster?
They're kind of the same, really.
Sine and cosine.
Sines and cosines. Okay, we'll do that. All right, so we're going to replace tangent with something in terms of sines and cosines. So look at your property sheet. Look for tangents near the top. What is tangent equal to?
Sine divided by cosine.
Sine over cosine. But this is squared. So what I'm going to place instead of this, I'm going to put sine squared over cosine squared. Does that make sense? Because it's tangent squared. So I'm replacing something of equal value. So that's my first step. So everything is in terms of sines and cosines. There's no other weird trig functions. A lot of you had that. Like this group here, you guys had that immediately. You had something, I think it was like what, secant or cosecant, and you had to go and replace things with sines and cosines to make that problem easier to look at. And then they went from there. Now, on this problem, do you agree that we have kind of a weird fraction over a fraction?
Yeah.
Let's do a quick reciprocal. Okay, so we're gonna do a reciprocal of the bottom. So we're gonna take the top times the reciprocal of the bottom. Because that's technically how you divide. You're dividing by the bottom, so I do a quick reciprocal. What do you get when you multiply these together? What do you get when you multiply sine squared times cosine squared over sine squared? What happens?
They can flip it to top and part.
Say it?
The bottom one cancel.
Yeah, these cancel. They cancel. They literally cancel out, so I'm left with 1 minus cosine squared. And that came down to what you both had. Both of your groups had the same style of problem. What is 1 minus cosine squared equal to?
Sine squared.
Sine squared. And that's your answer.
Do we still have our test today?
No.
What? Tomorrow?
Yeah. Hopefully. Kaylee's got to take hers yet. So I'm waiting for her to get them. So I think she said she was coming in tomorrow morning. Okay, we're good? Done for the day. Okay, hey, I would like those problems back in my envelopes, please, envelopes.
Hey,